EMF induced in a moving conductor. Any change in magnetic flux will induce an EMF in a loop. Here's a common scenario you might see in physics. To the left, there are metal rails in red that are in a uniform magnetic field. That field is pointing straight out of the page. Across the rails is a movable bar in light blue, also made of a conducting metal material. The rails combined with the movable bar create a complete loop. The blue bar can be pulled to the right or left by an external force, increasing or decreasing the area of the loop. We will now derive an expression for the EMF induced as the conducting bar is pulled to the right. The bar is being pulled by an external force at a constant velocity v. The area inside the loop is increasing. The amount of area being added to the loop, shown here, can be calculated by multiplying the length of this side, so the distance between the bars, and x, this distance, right? So we have this rectangle. That's the additional area being added. How far the bar has moved to the right is its velocity times the amount of time, v delta t. If you multiply this value by L, the distance between the rails, you get the change in area. Using Faraday's law to find the EMF induced in the circuit that contains the rail and the bar, where theta is 0 degrees, because we're assuming that the field is coming straight through the loop, and n equals 1, we have one loop, we can derive the expression. So change in flux over time is B times A over time because the magnetic field is constant, the only thing changing is the area. On the previous slide, we determined that change in area is BLV times delta T. The delta T's cancel, giving us BLV, pronounced bliv. Not really, but you can say bliv if you'd like. The induced EMF is in the direction that creates a current that generates a magnetic field that opposes the changing magnetic flux due to the increased area covered by the sliding bar. This is also known as motional EMF. Hence, there's a clockwise flow of current generating a magnetic field that is into the page. So let's see here, we have our rails. We have the external magnetic field was out of the page, but as this rail moves to the right, that means that the flux is increasing. So it's going to try to generate a field into the page to counteract the increasing amount of magnetic field lines going through here that are out of the page. So using right-hand grip rule, we can see that it must be clockwise current that starts to flow as soon as this bar is pulled to the right. This direction of the induced EMF is necessary to be in agreement with the law of the conservation of energy. If the current flowed in the counterclockwise direction, it would generate a magnetic field that adds to the increasing magnetic flux. This would increase the force due to the magnetic field, which would result in an increasing acceleration, which violates the law of conservation of energy. However, in the real case, an external force would be needed to be applied to the sliding bar to keep it moving to the right. The next few slides will show the force derivation of the motional EMF. We're going to examine this same scenario again, but now looking at the electric field. So, the rod is being pulled to the right by an external force. Using the right-hand rule, there is a magnetic force on the positive charges in the bar that push them to the bottom of the page. So remember, we have positive charges. In reality, positive charges don't actually move, but we can just pretend that they do for this derivation. Really, it's just the negative charges going up, but let's focus on positive charges. So when you're moving to the right, that charge right here, this little charge, has a velocity to the right in an external magnetic field. So using the right-hand rule, where you point your hand in the direction of velocity, you point your palm in the direction of the field, you see that your thumb points down. there would be a downward force on positive charges. And the negative charges are going to be pushed to the top. So this separates the charges in the rod. There's now positive charge at the bottom and negative charge at the top. This separation of charge creates an electric field that points up from the positive charges to the negative charges. And remember, it's actually the electrons that are moving, but because we're using conventional current, we can think of positive charges moving down as well. If the rod is moving at a constant velocity v and the charges are at equilibrium, so let's say we have a positive charge here and the force due to the electric field on that charge is equal to the force down due to the magnetic field, we have Newton's second law. So we have no acceleration. We're assuming these charges are at equilibrium, not accelerating. So we have that the net force must be equal to 0. Continuing the derivation, we have the force electric is going to have to be equal to the magnetic force. Well, the electric force is Q times E. The magnetic force on a moving charge is QVB. Therefore, we set those equal to each other. The Q's cancel, and the electric field is going to be equal to V times B. The two ends of the bar produce a constant electric field. So we have that the voltage difference between them is E times delta R, which is the distance between the bars. This is for a uniform electric field. So therefore, we can solve this for electric field and divide both sides by delta R, and we get E equals voltage difference over the distance between the bars. The voltage difference is the EMF. The distance between the bars is L, as we remember from before. And so we have two equations for the electric field. So we can set VB equal to epsilon over L and solve for epsilon, the EMF. And look at that, BLIV, BLV. Now to find the direction of the induced current in the loop. The bar has a net positive charge at the bottom and a negative charge at the top. When the two rails are connected by the blue bar, current will flow in this direction, conventional current, right? The electrons are actually going the other way, but we can pretend that we have positive down here, negative up here. That means positive charges are flowing clockwise. And this is exactly the same result we got earlier when we did Faraday's law and used Lenz's law to determine the direction of current.